Let's talk about protecting carboxylic acids and amines. Now, we've already talked about protecting alcohols, and now let's talk about carboxylic acids. You might say that or think that some of the reactions are very similar, but we'll look at that now. So, one of the things that we would want to protect against is the acidic character of a carboxylic acid. So if we wanted to have some kind of acid sensitive group on our molecule, we're going to have a hard time if we have an acid on it. So we need to have a way to cover that up. And one of the things that we could do is just turn it into an ester. And we've already discussed a few ways to do that. So we have an ester here, and we could just turn it into the methyl. Or we have a carboxylic acid, we'd like to protect it. Let's just turn it into a methyl ester. So we could just use Fischer esterification and turn it into the methyl ester. Now this will require acidic conditions, but maybe that's okay for now. Then we have an ester, the carboxylic acid has been protected, we've covered up the hydrogen essentially. There was another way that we talked about generating methyl esters, and that was with diazomethane. Now, this is a little less green than the Fischer esterification reaction, and we are dealing with an explosive reagent here. So if possible, I would suggest using the Fischer esterification method instead. But it will generate the methyl ester. Now, in both of these cases, since the product is a methyl ester, the deprotection is the same. So we'll just draw the deprotection step here. We just saponify it with sodium hydroxide. So step 1, use sodium hydroxide. Step 2, put the proton back on the carboxylic acid. And then we'll go back to our carboxylic acid. Now, of course, we will also need fairly basic conditions for this to happen. And so if we have something that's sensitive to acids or bases, we'll have to look elsewhere. Fortunately, this is not the only way we can protect a carboxylic acid. So it is possible to, instead of forming the methyl ester, we will do Fischer esterification again, but we'll choose a different alcohol. We're going to use benzyl alcohol. So here's benzyl alcohol. And remember, benzyl alcohol has one carbon off of the benzene ring. I know that used to confuse me as well. You would think that, this is called a benzene ring. You think, oh, benzyl. But a benzyl carbon is one carbon off of that. So it's one additional carbon. So try to remember that, and every so often I have to remind myself of that. Of course, we'll need our acidic conditions. So it doesn't quite get away from having to use acidic conditions, but the deprotection is a little different. And if we have a base-sensitive group somewhere on the molecule, then we may prefer this method. So now we've made this ester and protected our carboxylic acid. And then to go back to the carboxylic acid, of course we could use saponification, but that would kind of negate the whole point of using the benzyl alcohol, when we really could have just used the methyl alcohol, which is much smaller and more efficient. So in this case, we're allowed to deprotect using catalytic hydrogenation. And this will avoid the basic conditions of the sodium hydroxide. Now, catalytic hydrogenation comes with its own problems, and that would be if there are double bonds or triple bonds somewhere else on the molecule and we want to leave those alone, we're not going to use this method then. So the two products we're going to generate are toluene and the carboxylic acid in this case. So these are three ways to protect carboxylic acids. Now let's look at a couple ways to protect amines. All right. So we have an amine here. And the reason why we may want to protect amines is they are at least a little bit protic, but they're also somewhat nucleophilic. And so we might want to limit their ability to attack other things. And one of the ways to do that is to form it into an amide. And that will vastly reduce its reactivity. So we'll just use acetyl chloride, and then this will react with it, and we'll use pyridine as a base in this process. And then we will form a protected amine. And of course, these others could be hydrogens. It just depends. In all likelihood, they're probably not, because otherwise we would maybe start from a different point. So it's likely at least one of these is a carbon. I'm not sure why you would go through the trouble of trying to protect ammonia. All right, so here's our protected amine by converting it into an amide. And again, that will vastly decrease the reactivity of the nitrogen. And then it's possible to just hydrolyze this off with acid. And then we'll go back to whatever amine we started with. And of course, that is the point of a protecting group, to be able to cover up the functional group and then get it back at a later time. Now, this is one way of doing this protection, but there is a more famous and probably more versatile method for protecting amines. And that is the Bach protection method. And I'm forgetting what Bach stands for. I do have the structure though. So I'll draw the structure and not try to struggle through remembering what the name is for right now. So we need to use Bach 2O, and this is a reagent, and I'll draw what that looks like down below here. And we'll add some base, so sodium carbonate, a sodium hydrogen carbonate. And then we will Bach protect the nitrogen. You'll see this used a lot. And this also gets used in protein sequencing, like Edmond degradation. So, and again, same conditions, hydrolyzing it back into the amine. And let me just draw out what this Bach 2O looks like here. So this whole part is the Bach 2O. And so really just this portion right here is what's going to end up protecting it. So this carbon right here will bond to the nitrogen, and this is what we mean when we write Bach on it. And this is probably the most common way to protect an amine. You'll hear it referenced a lot. So that is how to protect carboxylic acids and amines.